Dr. Jan Gutenois is joining us from Tel Aviv University, and the title of his presentation is Hearing Space-Time Vibrations to Understand Math. Thanks.
Thank you for the introduction, Michal. So it's a wonderful pleasure to try to convince you that we can understand math by hearing space-time vibration. So first of all, what is a mass? The mass is a resistance to an acceleration. For instance, the mass of this Azrieli book is a resistance that I feel when I accelerate it. This is the inertia of the book, the mass of the book. This book contains zillions of elementary particles. There is more particles in this book than grain of sand in the whole Sahara Desert. The next question is, where does the mass of a single of those particles come from? The mass of a particle, during most of human history, we thought that it was an intrinsic property of particles. But today, we know that this statement is wrong. Instead, mass is an environmental effect. Since 1964, we know that mass of a particle is caused by the interaction with the Higgs field. The Higgs field is something that fills the whole universe, that fills this room, and will give mass to objects, to particles. In order to understand better what I said, I propose the following metaphor. The universe is like a gigantic aquarium. In this aquarium, water plays the role of the Higgs field, and fishes play the role of particles. Particles in Higgs field are like fishes in water. Fishes, when they move, they feel resistance due to the interaction of water with their body. For particles, this is the same. Particles, when they accelerate, they feel resistance due to the interaction with the Higgs field. You do not believe me? Okay, let's do a collective experiment. We just put our hand in front of us. Everybody, please, the hand in front of us, and we move our hand. We accelerate our hand, and when we accelerate our hand, we feel a resistance. We feel the inertia of our hand. That resistance that we feel is a direct evidence that we live in an aquarium of Higgs field. Congratulations. In 1 minute, you all became talented experimental physicists, and you made a major discovery. Actually, there is another way we can show that we live in an aquarium of Higgs field. We can create a wave in the aquarium. But this experiment will not do it here. This is done by professionals in Geneva, Switzerland. We have this ring of 27 kilometers of length buried underground. In this ring, they accelerate particles close to speed of light, and then they make them collide. Just to give you an idea of the power of that machine, if you take a mosquito and you accelerate it to the same speed as a particle in this ring, this tiny mosquito would have more energy than the fastest train in the world. So the collision is very energetic. And it's enough energetic to make the aquarium vibrate, to create a wave in the aquarium, a Higgs wave. And this wave is called the Higgs boson, and it has been produced and detected for the first time in 2012. A discovery, a major discovery, awarded, of course, by a Nobel Prize, 50 years after theoretical prediction. So now we are all convinced that we live in an aquarium of Higgs field, responsible for particles having a mass. Either we feel the resistance, either people, physicists, they create a wave and detect it. So now I would like to talk about an amazing property of this aquarium. This aquarium can boil. The Higgs field can boil. Actually, you should not be so surprised because you already know that water can boil. Water boils at 100 degrees. So why not the Higgs field? It's just another fluid, and evaporation is just a universal property of fluids. And indeed, theoretical modeling shows that the Higgs field can boil. This on the right is a numerical simulation done on supercomputer. And what you can see is Higgs bubble, which resembles a lot what happens in your kitchen when you prepare tea, when you boil water. The main difference, however, is the boiling temperature. the Higgs field boils at 10 to the 15 degrees, 1 and 15 zeros. This is a huge temperature. So we cannot heat a region of space at such a high temperature on Earth. Not yet. But in the early universe, just after the Big Bang, the temperature in the universe was around the temperature, even larger. It means that at some point, the Higgs field, the aquarium of Higgs field, was boiling 14 billion years ago, just after the Big Bang. My research is on finding observational evidence that this happened. Can we see that Higgs has boiled? I'm going to argue that we cannot see, but we can hear that Higgs has boiled. Think about the water metaphor again. Let's imagine you are watching TV and at the same time you prepare tea. You are not watching, but still, you know when water is boiling because you can hear the sound. Because boiling water makes the recipient vibrating. My research is on using the same strategy to hear that the Higgs field was boiling because boiling Higgs make space-time vibrating. Space-time can be understood as a recipient of the universe. And in the next slide, I'm gonna explain what does it mean for space-time to vibrate and what does it mean to hear it. We know, since Einstein, 1915, theory of gravitation, that space-time can curve. Earth, very massive, can curve space-time, and this impacts the motion of the moon. The moon feels the curvature of space-time, and then follows its trajectory, follows a slope, and this makes it turn, this makes it move along a circular orbit, and not a straight line. Now, take the most massive object in the universe, two black holes. Each of them curve the space-time, like this. And then make them move, make them spin around each other. This is how the space-time would look. This is something that evolves with time. Those are waves in space-time, vibration in space-time, called gravitational waves. And they have been discovered, detected for the first time in 2015, a discovery awarded by a Nobel Prize. This instrument is like a space-time microphone which can hear space-time vibration. Now what does it mean to hear space-time vibration? Because usually when you talk about hearing, we talk about hearing acoustic vibration. For instance, the sound of a guitar. Why is the microphone on the right can hear the guitar on the left? Because the vibration of a string of that guitar generates a vibration which propagates through air molecules. Air molecules act as a medium which propagates the vibration from the guitar till the microphone. For gravitational wave, this is the same. But instead, the medium is not the air molecules. This is a space-time which acts as a continuous medium which propagates the vibration from the black holes till the space-time microphone. And I had prepared a media which is the sound that this space-time microphone, gigantic space-time microphone, 4-kilometer microphone, compared to this one, which is quite small. So it's a gigantic amplifier. The sound that it amplifies is something like that. I will try to imitate it. This is the sound that the black hole make when they, at the end of their phase, when they merge in one big black hole. So this sound we could hear in theory with our ears, but it's so low amplitude that we need a gigantic amplifier, 4-kilometer amplifier, to hear it. My research is on using this strategy, this space-time amplifier, this space-time microphone, not to hear about black holes, but to hear when the Higgs field, the aquarium of Higgs field, was boiling. So theoretical model tells us that the aquarium of Higgs field was boiling 14 billion years ago. And what we do is we estimate what are the space-time vibrations which are generated by such a violent event. And then we look if space-time microphone can detect it. Unfortunately, this space-time microphone is too small, only 4 kilometers. So it's not enough to amplify the sound coming from boiling Higgs, because it has happened 14 billion years ago. The amplitude is smaller than black holes. But fortunately, in 12 years, there will be this gigantic microphone, 1.5 million kilometer microphone, which might be sensitive enough to detect vibration induced by the moment when the aquarium of Higgs field was boiling. This same aquarium of Higgs field responsible for particle having a mass, particle having a resistance to acceleration. Thank you for your attention.
Thank you, yeah. Questions? Start with Karen. Introduce yourself.
Hi, I'm Karen Klass I'm a postdoc at the Hebrew University. I study primate conservation. Very different. Can you talk a little bit more about this 1.5 million kilometer microphone that is going to be in existence in 12 years?
So I prepared a video of the experiment. I don't know if everybody's going to see it. So it's a triangle of satellites. I'm going to pass in front of everybody. It's a triangle of satellites which follows the Earth, which is a gigantic microphone which will follow the Earth, a gigantic triangle of satellites of 1.5 millions of kilometers, which follows the Earth. You see, it follows the Earth around the sun. So this will be in space. This will be gigantic, the biggest machine ever created by human beings. And this will try to probe if space-time vibrates. So it's a triangle. So I have the picture here. It's a triangle of 3 satellites, and each satellite is connected with the 2 others with laser beam. In red are laser beam. And those lasers, they measure very precisely. That's the best laser created by human beings. They measure very precisely the distance, the 3 distances of that triangle. Now, if space-time vibrates, the distance will vary over time, will oscillate. And the lasers are here to detect any possible variation of the distance of that triangle.
Can I just ask who's working?
It's me, no, I'm kidding. No, so this has been proposed by a few decades ago to probe. I mean, at the time of Einstein has predicted the existence of gravitational wave in 1916, 1 year after his theory of gravitation. But at that time, it was like science fiction. Nobody could imagine that one day a human being would be able to detect them, because the amplitude of those vibrations are very, very, very small. And so it's amazing that today we are able to design such experiments which can probe such a small amplitude, such a small vibration. And so this has been proposed, I think, in the first ideas in the 80s, 90s, by a physicist, a community of physicists. I cannot tell you exactly one name. It's like the community, people they started to talk about it, and many people worked on it. Everybody, I mean, a lot of people work on it. It's a very fashion topic. It's called gravitational astronomy. It's a bit the future of cosmology, because with gravitational waves, vibration of space-time, it's like having a sixth sense. We can now observe objects in the universe using space-time as a medium for information. So it's like a sixth sense. And the discovery in 2015, the first discovery of gravitational waves, has triggered a lot of research in that direction, obviously.
Okay.
Yes.
There's a lot of questions. We only have 5 minutes. So I'm going to take a number of questions, and then you answer them, and then we'll do another round, okay? So Daniel, Reuven, and Balthasar, and then afterwards we'll have another round.
I am Daniel. I'm a postdoc in the Weizmann, researching biology. So my question is that, with the 2 black holes, it's like a localized thing somewhere in the universe. It happens and it takes time until the waves get here. But like this boiling of the space-time, or like the Higgs boson, very long time ago, which I don't know, I imagine it happened everywhere. Like
Exactly.
how long do the waves prevail? And
Very good. So,
Wait, don't answer. Exactly, more questions, otherwise you won't have time. Yeah.
So my question is, assuming you detect this signal, how confident can you be that it's coming from Higgs boiling and not from some other source?
very good.
One last one about that, and then answer.
Okay, so my question is, what is the great scientific aims? Let's say we prove that the Higgs field was boiling. What do we learn from that?
I see. Okay. So thanks for all the questions. Very interesting. So first question, indeed, for black holes, the gravity waves are emitted by a very localized system. In the case of the boiling Higgs, if the whole aquarium in which we live was boiling, it means that the gravity waves are created everywhere. So they come from all directions. It forms a background. A background is, so there is no singular direction in which the signal comes from. It comes from all the directions. So it's a major difference. Then, for the next question, how can we know if we detect a signal that it comes from that? That's precisely our work, because we estimate what are the space-time vibration induced by such a dynamic. So we know the shape of those vibrations, the spectral shape of those vibrations, and then if we find something, if the spectral shape match, then we know with good certainty that it comes from that dynamic. And then for the last question, so what is it useful for? So there is a problem in this theory of the Higgs field. There are a lot of things that we don't understand. That we don't understand. There are a lot of puzzles, and this is related to the fact that gravity is the weakest force. So it is related to the puzzle that why a magnet is attracted by the fridge and not by the whole Earth. Two forces, magnetic, gravitation. Why magnetic force is so strong? Why gravity is so weak? Why is the Earth is so big? Fridge is so small. Earth should win. But it's not the case. So there is a huge hierarchy between forces. But quantum mechanics, according to quantum mechanics, force should communicate with each other and should harmonize and have the same intensity. Quantum mechanics predict that all forces should have the same intensity. It's not the case, and this is a big puzzle because the hierarchy problems. And we think that by understanding better this phase transition, because I can go into details, but it's related to that. That's the same model that predicts the hierarchy problem and the boiling Higgs. Thank you. Sorry for the technicality.
And if anyone else has a question, then this.
Actually, my question is to the sleeper what just said about phase transition. So I didn't understand the boiling Higgs. Does it mean there's a phase transition? Is the temperature exactly on a phase transition? Is this nucleotizing like water in a phase transition? So, what do you mean by boiling Higgs?
So,
Thank you for your answer. Any other questions? This is your last chance. Okay.
So thank you for the questions. So when the universe was born, at the Big Bang, the temperature was very high. So high that the Higgs was in an evaporated state, in a gas state with a very low density, and particles had no resistance to acceleration. They had no mass. Universe was born without mass. So if there is no mass, there is only light. So universe is born with only light. And then, as the temperature cooled down, the Higgs start to go from gas to liquid during a phase transition. And this phase transition, the question is, how does it take place? And theoretical modeling tells us that it takes place via the same way as for water, the liquid gas transition for water, it takes place via bubble nucleations. And then those bubbles, they are very energetic and they collide with each other. And this can be understood as motion of massive objects, like motion of black holes, which were massive objects. Motion of black holes could generate gravity waves. So this motion of bubbles, energetic objects, also generate gravity waves. Thank you.
Thank you very much. Yeah.
Thank you.